A very good morning to all the first year students, viewers. Welcome to the webinar series organized by Telangana State Model Schools. In the previous physics session, Mr. N.V. Subramaniam Garu had introduced thermal properties of matter and discussed the concepts of temperature and heat, scales of temperature, measurement of temperature and thermal expansion as well. Today we have with us Mr. N.V. Subramaniam, a passionate science teacher, a distinguished speaker, who is working as a PGT Physics in Telangana State Model School, Turkapalli, Yadadri, Bongir district, who is very familiar to you. So good morning, sir.
Good morning, madam.
And I request you to start your session, please.
Yes, madam. Respected Principal Madam, Coordinator Shrikant Garu, Principals and children attending the webinar session. Good morning, all of you. Today I am here to present the thermal properties of matter, part 2 session of the webinar. In the part 1, we have dealt about the topics temperature, measurement of temperature, heat and temperature, thermal expansion. Today we will deal about continuation of thermal expansion, dealing with liquids, gases and related expressions, and also the expression to calculate heat. Let us start the session, children. The learning objectives for this session: thermal expansion of liquids and gases, actually, anomalous behavior of water, thermal expansion of gases, ideal gas equation, and also measurement of heat. Okay, so these are the learning objectives for this session. The degree of hotness or coldness of a body is called temperature. So we are recalling some information what we have given earlier. Heat is a form of energy that is transferred between a body and the surroundings due to the temperature difference between them. The formula to convert Fahrenheit into centigrade is Tf minus 32 by 9 is equal to Tc by 5. Tf is the reading on the Fahrenheit thermometer. Tc is the reading on the centigrade thermometer, that is also known as Celsius. Okay. Most substances expand on heating and contract on cooling. So these are the things which we learned, and we have already dealt about some important and interesting topics in our earlier webinar, like expansion of solids. We know that generally solids expand on heating. Yes or not? Solids expand on heating. And I have explained to you some interesting applications, like why they are leaving a gap in between rails. Okay. And similarly, I have also explained what happens to the time period of a pendulum. Very important questions from exam point of view. So today I am going to deal with one more question which is important from the exam point of view, a bimetallic strip. Okay, bimetallic strip. So in the diagram you are seeing first figure, if you see carefully, blue color, yellow color. Two strips I am showing. Strips means actually nothing but two small metal sheets. Okay, metal sheets are known as strips. Here, if I am showing you, let us say blue color is one metal sheet, yellow color is another metal sheet. Okay, so let us say, for example, children, This blue color is the brass. Okay, this is brass. And this yellow color strip is the iron. Before I start explaining, I want you to remember these values. Coefficient of linear expansion for brass, which is equal to, if you remember, 1.8 into 10 to the power of minus 5 Kelvin inverse. Similarly, brass and next one what I am telling you, iron. Alpha value for the iron is 1.2 into 10 to power of minus 5 Kelvin. So here alpha brass is more than alpha iron, which means brass expands more than iron. What will expand more? Brass expands more than iron for the same rise in temperature. So this property is called differential expansion of the metals. Okay, differential expansion meaning the one metal expands more compared to the another. That is called as differential expansion. So in the second diagram, if you see, when I am heating them to the same change in the temperature, let us say brass, how much I am changing the temperature, iron also I am changing same temperature range. That means delta T is same for both of them. Then you are seeing that brass expansion is more, iron expansion is less. See the second diagram, there is a gap in their expansion, which means iron expansion is less, brass expansion is more. Okay, all of you. So this point you keep in mind. Now see the third diagram, children. So what is a bimetallic strip actually? It is a strip in which the two metals are welded together, brass metal and iron metal. Then student will get doubt in the mind. Sir, brass and iron only you are using. Can I use other metals also? Yes, children, you can use any metals what you want, but two different metals you must use. Okay, so that you are using the principle of differential expansion. Then you weld them together. When you weld them together, children, and heat it, then what happens? One will expand more, one will expand less. And since there is welding of the joints, it begins to bend. It begins to bend, children. So in the examination, they are asking, what happens to a bimetallic strip when it is heated? Answer what you will tell. A bimetallic strip, the joints are welded. So when they are heated, one metal expands more than the another. So it bends as shown in the diagram number 3. This is how you must write the answer. Okay. Then fourth diagram you observe carefully. The bimetallic strip is fixed in one side. It is fixed, children. It is fixed in one side. And when you heat it, what happens? It bends as shown in the diagram. You see, it is bending like this. Yes or not? So the bending will be like this. And I will explain to you one interesting property of this fourth diagram where we will use it. Okay. So I hope the screen explanation is clear, all of you. Shall I go to the next screen, children? Now, so what is bimetallic strip? Bimetallic strip consists of two different metal strips welded together. It works on the principle of differential expansion of the metals. When it is heated, it bends due to the differential expansion of the metals. Okay, when it is heated, what happens? It bends due to the differential expansion of the metals. So now when it is cooled, it returns to its original position. So on cooling, what happens? It becomes again come back to the original position, which is a dotted line. Understood? So, bimetallic strips are used in thermostats. So, what are these thermostats? I will explain to you. Okay, just a minute. Let us explain what is the meaning of a thermostat, children. Now, I will take one small example to make you understand, children. Let me draw the bimetallic strip first of all. Okay, this is the fixed one, right? This is the bimetallic strip with brass on one side, okay, iron on another side. So here I am drawing one pointer, okay. This pointer you are seeing, okay, pointer. You are able to see pointer. Then this pointer is connected to supply. Supply means electrical supply, okay, okay. I am asking one small question. Tell me before I conclude. This is a switch. This is the current supply. Let us say plus and minus. The moment I switch this on, when it is on, what happens? Think current starts flowing. Okay, current starts flowing. Now, did you see iron box, children? Yes, electrical iron box, which you will use in your home to iron the clothes. Then, if you switch on the current, what happens? One red light will be on in that, right or not? So, the current is flowing. As the current flows, iron box starts getting heated because of the heating element. Now, when the iron box is getting heated, inside the iron box, this bimetallic strip based thermostat will be there, children. This bimetallic strip also starts getting heated. When it starts getting heated, after reaching a particular temperature, it bends away like this. That means the bimetallic strip has bended. Then what happens to the connection with the pointer? The pointer connection is lost. When the pointer connection is lost, what will happen? Then automatically what happens is, even though the current is on, you see the switch is on, children. Switch is on, but the current does not flow into the bimetallic strip. And here if we are having heating element, the heating element does not receive heat, does not receive the current actually. So in your iron box, you might have seen the red light automatically goes off, which means that the current supply has been cut off automatically. So that means that the iron box has reached the required temperature. Thermostat meaning which maintains constant temperature. So once the temperature required is reached, the bimetallic strip bends away and cuts off the current. Okay, once it cuts off the current, what happens? The iron box begins to again cool down, and again it will go back to its original position. And when it cools, it goes back to original position. And again current is restored because it will touch the pointer. So whenever bimetallic strip touch the pointer, let us say this is the pointer. Whenever bimetallic strip touch the pointer, current again starts. That means the red light will again on. So this you might have seen already in your home. In your home, you might have observed the working of iron box, electrical iron box. We will call iron box. It is actually press iron to press the clothes. So that press iron will have a thermostat like this, which will maintain constant temperature. And the thermostat actually contains a bimetallic strip. I hope now you understood how the bimetallic strip is helping in working of the press iron. Same thermostat is also used in the refrigerators, children. Okay, you might have observed refrigerator automatically switches off, automatically switches on. because of the working of the thermostat. Okay, so I hope this explanation is clear to all of you, right? Let me move on, children. So last class in our um, thermal expansion, we talked about alpha. Alpha is we are having linear expansion alpha, next areal expansion alpha, and volume expansion alpha. Three types of alpha I explained to you. Do you remember? Yes? Do you remember? What are the three types of expansions I told you? Linear expansion coefficient. What is linear expansion coefficient? I told you delta L divided by L into delta T. Next, alpha aerial calculated by formula delta A divided by A1 delta T. Next, alpha volume calculated by using what is the formula? Delta V divided by V1 delta T. Right or not? So, that is V1, or I can just write V also. Here also, A delta T, V delta. Okay, so these are the formulae we are using for linear expansion coefficient, areal expansion coefficient, volume expansion coefficient. And we told you that alpha aerial will be 2 times alpha linear. Similarly, alpha volume will be 3 times the linear coefficient. Okay, this is what we told you already, right or not? But we did not prove it. Now let us try to prove this formula. Okay, alpha aerial is 2 times alpha linear. I will prove and show to you. Shall we do that, children? Yes. Okay. Okay, right. For that purpose, what I will do is, you see here carefully. Okay, see here carefully, children. Consider a square, a metal square plate. Okay, it is a plate I am telling you, metal square plate. Okay, what is the side of this plate? 1 meter. Side 1 meter, 1 meter, 1 meter, 1 meter, 1 meter. Okay, 1 meter. This I hope is clear to you. Now, what I am doing is that means original length. Let me write the steps to you. Okay, original length of this particular square plate, capital L, is equal to 1 meter. Okay, now what I am trying to do is I am heating this square plate. Now what I am trying to do, heat the square plate. Okay, heat the square plate such that there is 1 degree change in the temperature. That means delta T is T2 minus T1. No, that is how many degrees centigrade I am changing the temperature. 1 degree centigrade change in the temperature. Then you all know, even if I am changing 1 degree also, this metal will expand slowly, little bit, it will expand on all the sides. Even for 1 degree also it will expand, right or not? That means square plate expands. Square plate expands. Okay, children. When square plate expands, this is first point. This is second point. Okay, when square plate expands, what happens to the length? It will also change. Then coefficient of linear expansion. What is that? Coefficient of linear expansion. Coefficient of linear expansion alpha L I can write as delta L divided by L into delta T. Okay, alpha L is alpha L, keep it like that. Delta L I don't know. Okay, now let the children, let the new length is I am writing here. This is original length. New length, let us call it as L dash. New length is what? L dash. This length will increase now like this. Let me draw like this. So that dotted line you are seeing, children. This dotted line is the expanded square plate. Okay. This new length L dash. Okay. So L dash is new length. So here delta L I am writing as usual. By original length, how much you see all of you? 1. Write 1. Into delta T, how much? 1. Write 1. Then continuing here, I am drawing one line so there will be no confusion. Okay. Alpha L is equals to delta L by 1 into 1, 1. Okay. Anything by 1 is delta L. So delta L is equals to, how do you calculate delta L? Tell me. First of all, it will be equal to new length minus old length. Okay. Children, how do you calculate the value of delta L? You tell me, all of you. That is the new length minus old length. Old length is L. New length is L dash. So L dash minus 1. Okay, children. So here I will get, this is L dash minus 1. Minus 1, if it comes this side, it will become plus 1. 1 plus alpha L is the value of, okay, L dash. Let us call this as equation number 1. So L dash value is 1 plus alpha L. Are you clear? Now I am going to the next screen. Are you clear with what is there in the screen? Right. Now, again come back to our original diagram. Here if you see, this square plate you are seeing, this square plate is expanding from this position to this position. That means its area is changing or not changing? Changing. So let us say original area. Original area. Children, tell me how you will calculate the area of a square? Side into side. That means L into L. That means L square. That means area is, original length is L, L square. L is how much? 1. 1 square. 1 square how much? 1. So 1 meter square is the original area. Remember, what is the original area? 1 meter square. So here I am writing, let the original area is 1 meter square. Now let the new area, expanded area, is A dash. Then A dash will be what? Again, that is also square only, no. Its area must be L dash whole square. That means A dash is equals to, what is L dash value? 1 plus alpha L. Don't forget. 1 plus alpha L whole square. And you know, all of you, how to calculate the value of this one. That is A plus B whole square formula. A square plus B square plus, what is the value? 2 into 1 into 2AB. Here I want to tell one important point, children. Very important point. I will take one blank screen and explain. Just hold on. We got actually a1 square is equals to, that is sorry, a dash square, no? We are taking a dash. So, if you are seeing a dash square is equals to, we are having L dash square. That is 1 plus alpha L whole square. And this is what we wrote, 1 square alpha L square plus 2 into 1 into alpha. That is 1 square is 1, alpha L square is alpha L square. 2 into 1 into alpha L will be the 2 alpha. Here only I want to tell you one important thing. For example, let us say square plate is made up of brass. Brass square plate I am considering. Consider what type of square plate? Brass square plate. Can you tell me what is the value of alpha for brass? Just now you wrote 1.8 into 10 to power of minus 5. Then what will be alpha L square? Tell me. 1.8 square. What is 18? 18s are. Do you know 18 18s are? 8 8 64. 8 1s are 8 plus 6 14. What are no? 1 8s are 8. 1 1s are 1. That is 4. Okay, this is 2 plus 1 carry 3 times. That means 1.8, 1.8. So we will get 3.24. 3.24 into 10 power minus 5 also we must do square, no. That means 10 power minus 10. So alpha L square 1.8 square if you do you will get 3.24. 10 power minus 5 square if you do 10 power minus 10. Children, can you guess what is this value? Actually, this value is, if you write in decimal point, this is how much? Tell me, how much is this? Can you guess? 1.8. 0.00018. Am I right? That's right. Then what about this one? 0 point. Tell me how much? 0.0000000. Am I right? 7 zeros. And is it much more? This is 324 into 10 power minus 10. 10 power 24 10 power minus 12. 18 into 10 power minus 6 or 324 into 10 power minus 12, which is that means you will get 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9, 0, 9, 0, 2, 0. This is the value. See here, this is itself very small. This is very small. Yes. Then this is very, 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 very small. Very, 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 very small value. That means we can neglect the value. Alpha L square value is neglected. Okay, neglected. Neglected means you can leave it off, children. Alpha is very small. Alpha L square is much more smaller. Okay, alpha L square is much, much smaller. So, as alpha L is small, alpha L square is very, very small and neglected. What are we doing? Neglected. So neglected means This formula, let us call it as equation number 2. Equation 2 will become a dash is equals to, this 1 square is 1 only, so write 1, plus 2 into 1 into alpha will become 2 alpha. Let us call this as equation number. Now I am asking one small question. Just now you wrote alpha aerial. You learned or not? Alpha aerial is delta A divided by A into delta T. Original area into change in the temperature. Okay. Already you know delta A, how many you must calculate? A dash minus A by A into delta. What is the value of A dash? See here, 1 plus 2 alpha. 1 plus 2 alpha. Minus A value how much? 1 meter square. By again A value how much? 1. Into delta T value how much? 1. That is alpha aerial. I will call it as alpha A. Alpha A is equals to minus 1 plus 1 cancel. This is 2 alpha divided by 1 into 1 is 1. That means 2 alpha L actually, linear. That means I got alpha A is 2 alpha L. Are you clear, children? Alpha A is how much? 2 alpha L. So aerial expansion is double the linear expansion. Like that, alpha volume will be triple the linear expansion. Remember, this you try to prove homework. This is homework for all of you. Alpha volume is 3 alpha L. Okay, instead of here A dash is L dash square, right? V dash is equals to original volume is L dash cube. Then you take cube, children. Excuse me. Then you take cube. Instead of square plate, take the cube and you will get the answer. Okay, you will get the answer. So, I hope this explanation is clear to all of you. So, I finished actually expansion of solids. Now, let us try to go ahead and let us try to study about expansion of liquids, children. Okay, expansion of liquids. So let me continue with our topic. Okay, so 1 minute. Right. So now if you see, we are having an interesting video coming here. What is that video? Let us see. Let's play this video. 1 minute. There is a small video coming here. Excuse me. To disable the pointer. Just a minute. So video is playing. Please see carefully. I will play the video from variable required files. Question you see all of you. Does water expand on heating? This is the question. Okay. Come back to my explanation. Listen carefully. See, what did I do here? I took water in a bottle. I am adding color to it. Okay. Take a small cap. Put a cut refill to it. Okay. You all know pen refill you can use. Put it inside a bowl. Okay. Now pour hot water, boiling water. Will the water rise through the refill? Let's see. Very interesting experiment. So no. From this experiment, we can gain a lot of things, children. Let us try to understand. First, what will happen? Will the water directly receive the heat or bottle will receive the heat? The bottle receives the heat, then the water inside will receive the heat. Then you see water level, what is happening? It is rising. Lovely experiment. Yes or not? So what does this experiment show to us? It shows to us that, can you try this with other liquids like oil and alcohol? Yes, we can try. So one lovely activity, yes or not? Once again, if I want to see, I will show you. You see here. It's only hardly half a minute. You can just see it and learn from it. See, that means level of water is rising means, is it expanding or not? Yes, that shows that liquids are expanding. They are expanding. So liquids expand more than solids, children. Liquids do not have, very important point, liquids do not have linear and areal coefficients of expansion, as they do not have length and area of their own, and they take the shape of the container in which they are filled. Okay, this is very clear to all of us, yes or not? You know that whenever we keep a liquid inside a container, can you heat a liquid directly? No, you need a container. That means liquid don't have length, liquid don't have area of their own. They take the shape of the container. That means they will have only volume. So when they have only volume, that means that we cannot define linear and areal coefficients for the liquids. We can define only volume coefficient for the liquid. This is a very important 2 marks question for the exam. Liquids do not have linear and areal coefficients of expansion, as they do not have length and area of their own, and they take the shape of the container in which they are filled. Okay, coefficient of volume expansion of liquid is given by same formula, alpha V is delta V by V delta T. Okay, same type of formula for solids as well as liquids. Is this clear? So now I want to explain one important topic which has a lot of significance in science, even in nature also. Anomalous behavior of water. Anomalous. The word anomalous means peculiar or strange. Peculiar or strange. So what is strange here? What is strange about the water? You know that whenever you are talking about water, generally what happens? Generally, generally liquids expand on heating. Right or not? Expand on heating. And what is the opposite of this? Generally, liquids contract. Contract means the volume decreases. Contracts, contract on cooling. Okay. Expand on heating means volume increases. Contract on cooling means volume decreases. Okay. Keep this in mind. What happens to water? Water is very special, children. Water is very, very special. What happens is, I will tell you. See. Let us say I am heating water from 0 degrees centigrade up to 100 degrees centigrade. From where to where? 0 to 100 range. I am heating the water. What I am doing? Heating the water. Okay? What happens to water is 0 to 4 degrees, it contracts actually. And 4 to 100, it expands. That means in the range 4 degrees to 100 degrees, it behaves like all liquids. But 0 to 4 degrees, its behavior is peculiar. Similarly, cooling, I will explain you. See, cooling. When you cool the water, what happens? Let us say I am cooling from 100 degrees centigrade backwards up to 0 degrees centigrade. Cooling, I will draw reverse diagram. Okay, like this. Reverse means cooling process. Right? Now I'll ask one question. What happens? 100 to 4 degrees, it will behave like all liquids. That means it contracts. But 4 to 0 degrees, it expands. It expands, children. What happens? It expands. This behavior is called anomalous expansion of water. What is this known as? Anomalous. Anomalous expansion of water. Anomalous expansion of water. Okay. So because of this behavior, what happens is expands. It expands from where to where? 4 to 0 degrees. When you are cooling from 4 degrees to 0 degrees, it expands. That means volume goes on increasing and density goes on decreasing, because you know, all of you, density is always given by mass by volume. So if volume is increasing, density is decreasing. That means the density of water is more at 4 degrees, actually maximum at 4 degrees, and it is minimum at 0 degrees. It's less, that means minimum value. That means in the range 4 degrees to 0 degrees, density of water decreases. That means density of water at 4 degrees is more than 4 degrees centigrade, is more than density of water at 3 degrees centigrade, is more than density of water at 2 degrees centigrade, is more than density of water at 1 degree centigrade, more than water at 0 degrees centigrade. Okay, all of you, 0 degrees centigrade water also can have. So this means that this is having maximum density, this is having minimum density. You know, ice floats on water. If I put ice, if I am putting, this is water, let us say. If I put ice blocks, they will float on the water. Yes or not? They will float on the water. Why? Because ice density is less than water density. Yes or not? Ice density is less than water density. So this property you remember, children. So did you understand anomalous expansion? I will explain the actual importance of this. Let us see. Generally, liquids contract on cooling. That is, their volume decreases and density increases. Okay. Water contracts when cooled in the range 100 degrees to 4 degrees. This is normal behavior, I explained. But water expands when cooled in the range 4 degrees to 0 degrees. This is known as anomalous expansion of water. What is this known as? Anomalous expansion of water. Okay, children. So water has maximum density at how many degrees? At 4 degrees. And its density decreases in the range 4 degrees centigrade to 0 degrees centigrade. In the examination, you must write all these points, children, for the 4 marks question. Okay. Now you see, all of you, what is happening to the density of water? If you see density of water, if you see the density of water, actually, it is more at how many degrees centigrade, you see? This is maximum value, no? And if you see, it is having maximum density at how many degrees? 4 degrees. Then 3 degrees density is less than 4 degrees. 2 degrees density is less than 3 degrees. 1 degree density is less than 2 degrees. 0 degrees density is less than 1 degree. This is having lot of importance, children, density of fresh water. So let me explain one important application of this. Okay. So advantage of anomalous behavior of water to aquatic animals. So what happens to the aquatic animals? Let us see. Let us try to understand. Aquatic means what? Fish and all those things living inside the water. Okay. Whatever animals are living inside the water, they are known as aquatic animals. Okay, they are known as aquatic animals, children. So if you are having, you know that in cold countries, the temperature decreases very heavily in winter season, right or not? And you know that freshwater lakes and all those things. Lakes means no, small lakes will be there in villages also. So in that particular lakes and all those things, ponds, the water begins to freeze, children. That means let us say, for example, this is the lake. Okay, this is the water. Okay, this is the lake. Let us say, right now in winter season, in winter, in winter, what happens? You tell me. Temperature starts decreasing. Temperature of the water decreases. Temperature of water decreases. And slowly what happens is the water's temperature when it decreases, when it reaches 4 degrees centigrade, the water which has reached 4 degrees centigrade, that has maximum density, children. So what happens if density is more? Will it sink or will it float? It will definitely sink. You know that if you put a coin inside the water, it will go to the bottom of the water because density is high. Like that, 4 degrees centigrade water. Water at how many degrees centigrade? 4 degrees centigrade has maximum density and it will sink to the bottom. Maximum density and sinks to the bottom. That means if this is the diagram of the lake. At the bottom of the lake, what happens is you will have 4 degrees centigrade water. Then the water which attains 3 degrees centigrade, that will also go to the bottom, but it will form a layer above the 4 degrees centigrade, because 3 degrees centigrade water is having lesser density than 4 degrees centigrade. So it will be above this one. Like that, some water might have attained 2 degrees centigrade, that will come and settle above the 2 degrees centigrade. Like that, here you will have 1 degree centigrade layer. And at the top, you might have 0 degrees centigrade. That means you might think that at the top it has become ice. Don't think that the complete pond has become ice. Inside you will have warmer layers of water. Are these cold waters or warm waters? Warmer layers of water. Okay, children, they are warmer layers of water. That means the fish will be compulsorily staying in the warmer layers, children. So, if you see carefully, because of the anomalous behavior, the bottommost, so these are the fish, children. Okay, and the fish will stay in which layer? The warmer layers. They prefer to stay in the warmer layers. And they are surviving because of the anomalous behavior of the water. Fish survive the extreme winter. Fish survive because of anomalous behavior. Okay, so nature has provided an excellent mechanism for the living beings to survive. Anomalous behavior of water. Okay, is this clear? This is what you must write in the examination. So, in the anomalous expansion, we see that 4 degrees centigrade water sinks to the bottom. And on the top of this 4 degrees centigrade, we will have 3 degrees centigrade layer and so on. And these warmer layers will allow the fish to survive. Are you clear? So, as the density of water is maximum at 4 degrees centigrade, water from the bottom of the lake remains at 4 degrees even though the surface of lake freezes. This allows marine animal to remain alive and move near the bottom. Okay, so these are actually superimposing, but I suppose you are able to see, right? Uh, you can refer the textbook also. Let me move on to the next topic here. I suppose clear? Yes. So now I will explain about one more important question. Again, student is getting doubt in the mind. Sir, you talked about expansion of solids, and we proved that solids will expand. You talked about expansion of liquids. We proved that liquids can expand. Now again, student will get doubt in the mind. Can gases expand? That is the question. Yes, children, gases also can expand. Let me explain with the help of this example. The lovely activity. We are tying a balloon to a bottle and the bottle is empty. That means it is having air actually. If I pour hot water, what is happening? Did anybody blow the balloon, air in the balloon? No. The air inside the bottle is expanding. And because of the expansion of the air, the balloon is blowing and it is expanding. The balloon is getting inflated. Similarly, will the air contract on cooling? Let us try to see. We have taken the balloon with the air in it and I am putting it inside a bottle with ice in it. Okay, ice and water solution. And it was very difficult to put the balloon inside that bottle. Now you see what happened to the size? It decreased because of the lower temperature. Right or not? That means it proves very clearly that the gases will expand on heating. So gases also can expand on heating, children. Okay, so gases expand more than liquids and solids. For a given mass of a gas, its volume, pressure, and its absolute temperature. Absolute temperature means measured in Kelvin. Describe its behavior. Okay, for a given mass of gas, its volume, pressure, and absolute temperature describe the behavior. So, first let us learn about Boyles Law, children. For a given mass of gas, pressure is inversely proportional to its volume at constant temperature. This is known as Boyles Law, one of the most important questions for exam. 2 marks. State Boyles Law. For a given mass of gas, the pressure P is inversely proportional to its volume V at constant temperature. P is proportional to 1 by V, provided temperature remains constant. Okay, but 1 by V means what is the meaning of that? When volume increases, pressure decreases. Inversely proportional means what is the meaning, children? Pressure increases, volume decreases. So if we remove the proportionality sign, we will get constant. I can write P is equal to K into 1 by V. Cross multiply, children. If you cross multiply, if you cross multiply Okay, you cross multiply. P into V is equals to constant. What am I getting? P into V is equals to constant. So this I can write now as P1 V1 is equals to constant. Similarly, I can write P2 V2 is also equal to constant. Okay, then right hand side are equal. I can write the formula as P1 V1 is equals to P2 V2. This is a formula you use whenever you are using problems, whenever you are solving the problems in expansion of gases. I hope Boyles Law is clear, but student is having already doubt in the mind. For everything you are showing an activity, for this no activity. Yes, I got an activity for this also. See here. You are seeing the gas molecules here. Black color dots are gas molecules. That means the gas is there inside a cylinder. Okay. If you see here carefully, as I increase the weight, these are the weights children. There is a piston, movable piston here. Yes or not? When I put more and more weight, pressure on the gas will increase and the piston will go down, volume will decrease. That means pressure increases, volume decreases. That means as I add more and more weight to this one, what will happen, children? In the, if you see, as I put more and more weight, the pressure is increasing, volume is decreasing. And see the graph, children. As the pressure increases, volume decreases. As pressure increases, what happens to the volume? It will decrease. That means if you see the graph between pressure and volume, this is volume, this is pressure. Okay, let's say values I'm taking like this. Okay, 1, 2, 3, 4, 5, 6 like this. Okay, in Newton per meter square. This is, let us say, volume values 1, 2, 3. This is only sample values, children, not exact values, to show you when the pressure is less, volume is high. But as you increase the pressure, volume starts decreasing. That means what happens? The graph will come like this. This is actually called isotherm because it is a graph drawn at constant temperature. Okay, it's graph drawn at constant temperature. It's a rectangular hyperbola. Okay, so if you see carefully, pressure increases, volume decreases. This is at constant temperature. What behavior? At constant temperature. This behavior is known as Boyles Law. Okay, so let me move on. Let me explain one more law to you, Charles Law. This I need not explain, children. Already you saw here in this activity. 1 minute. You saw in this activity, no? See this? Just a minute to see this activity. Already I have shown this activity to you. As the temperature increases, what happens to the volume of the air inside? It will increase. Yes or not? That means that this I already have shown you with the help of an activity. This means that the volume and temperature are directly proportional, provided pressure remains constant. Okay, provided pressure remains constant. That means for a given mass of a gas, volume V is directly proportional to its absolute temperature at constant pressure. Okay, at constant pressure. When the pressure is kept constant, volume and temperature are directly proportional. That means V is directly proportional to T. If we remove proportionality, what we will get? Constant. Then V is equal to KT. Okay? Or if you bring T this side, V by T is equal to constant. So if V by T is constant, I can write this as V1 by T1 is equals to constant, and also I can write V2 by T2 is equals to constant. When right hand sides are equal, I can write V1 by T1 is equal to V2 by. This is a formula you have to use whenever you are applying Charles law in problems. Okay, for a given mass of gas, volume is directly proportional to its absolute temperature at constant pressure. Okay, so I suppose two laws you have learned. One is Boyle's law, another one is Charles law. So if I if I am asking you a small question, in Boyle's law, temperature is constant. In Charles law, pressure is constant. Now, for suppose nothing is constant, then student will get doubt. No parameter is remaining constant. Then what will happen? Then I can use something as Gauss, something called as Gauss law. Something called as ideal gas equation. So before I go to that, Charles law graph is being shown to you. Volume and temperature are directly proportional. The graph will be straight line children. Clear? The straight line. Are you clear? So now I'm coming back to the question what I was asking you. Ideal gas equation. So what is this ideal gas equation? You studied already that in Boyle's law temperature constant, Charles law pressure constant. Nothing is constant means what will happen? All three parameters will change. Pressure is changing, volume is changing, temperature is changing. Then how to study about the gas? Then the perfect equation for that is ideal gas equation. Let us learn about it, children. So PV is equal to constant. You learned already from which law? Boyle's law. V by T is equal to constant. Already learned from Charles law. Then I can write using these two. PV by T is a constant. Okay, children. This means that here this K is there, no? This constant K, it is same for all the gases. If you take 1 mole of a gas at STP conditions, okay, at STP conditions, this K value, actually this K value will be called as universal gas constant. So for 1 mole of gas, the constant is called universal gas constant. So PV by T is equal to capital R. Okay, what is it called as? Capital R. So this K is known as what? Universal gas constant, capital R, for 1 mole of gas. Okay, for 1 mole of gas. And you know that for 1 mole of gas, the pressure value, volume value, and temperature value, if you are substituting at STP conditions, then R value you will get as a universal constant. R is 8.314 joule mole inverse Kelvin inverse. Okay, so if we are seeing here, why we are calling it as universal gas constant means this constant is the same for all the gases. That is the reason why I wrote for 1 mole of a gas. I did not tell this gas or that gas. It is the same for all the gases. Okay, children? That means for all the gases, this law is applicable. PV by T is equal to R. So this is for 1 mole. If I am taking more number of moles, then now I must write. So if I cross multiply, PV is equal to RT, where universal gas constant capital R is this one, 8.314 joule mole inverse Kelvin inverse. Now, for mu moles of a gas, PV is equal to mu RT. So this final equation you remember, children. It is for any number of moles. You can take for 1 mole. If you take for 1 mole, if you take mu is equal to 1, number of moles is mu no. If mu is put as 1, if mu is put as 1, then the formula will become PV is equal to RT. That means this value will be there. Understood? Clear? So Ideal gas equation, very important for all the examinations. Please remember carefully. Okay. So I'm coming to the last topic for today. That is specific heat capacity. Right. Let us try to look at this. Till now, what was the discussion we were doing? We were talking about only expansions. But what is the method to calculate how much heat has been absorbed by the body? Let us call heat as Q. Let us mention heat from now onwards as Q. Heat gained by the body or heat lost by the body. Heat gained or heat lost by the body, let us call it as Q value. Then Q value, what is the formula? What is the formula for Q value, calculating Q value? How to calculate Q? Okay, so this is what I am going to teach you now. Expression for the amount of heat gained or lost. Okay, for that, see here this activity, let us see. Here you are taking water, children. How much? About 0.031 kgs of water. Okay, pour hot water into a beaker. Okay, how many beakers you are having here? Two beakers, children. In one beaker you are having normal water. In another beaker you are having oil, same mass. Okay, so how many beakers you are having? Actually, you are having, a minute. So we are taking same mass of, what is that? Just a minute. Let the you observe the activity. I will explain to you in a moment to all of you. First activity. We were taking same mass of water and oil. Water and oil in the beaker. And let us say we are heating them. When you heat both of them, they are observing the rising of the temperature in thermometers. If you observe, the rate of rising temperature of oil is higher than the rate of rising temperature of water. That means delta T is more for oil than delta T for which one? Water. So oil is getting heated faster when compared to water. So what could have been the reason for this? Let us try to see. Okay. Then if you see carefully, you continue viewing the activity. See here. So we have seen till here already. Complete experiment you observe, children. Then we will explain. Okay. By observing the rise in temperature of thermometers, we can say that rate of rise in temperature of oil is higher than that of the rise in temperature of water. Okay. If we continue the activity, again what they are doing, let us see. Okay. The rate of rise in temperature depends on the nature of the substance. That is evident. Yes or not? So to understand that nature, let us do some more activities, children. What is that activity we are trying to do? Relation between mass and heat. Okay, let us see. So we are taking two beakers, two thermometers, two stands, two lamps, two rubber cocks. Okay, and you see carefully. In one beaker I am taking 100 grams of water. In another beaker I am taking 200 grams of water, and I am heating both of them. I am heating both of them. And if I observe the readings of both the thermometers, if I observe the reading of both the thermometers, let us say for about 10 minutes, let us say, okay, so they are observing, they are taking the time, okay, and they are observing, noting down the temperature readings, children. So they are seeing that lesser water temperature rise will be faster, whereas more water temperature rise will be slower. That means, what is the meaning of this? We can notice that the 200 grams of water is taking more time when compared with 100 grams of water to rise to the same temperature. That means, what does this mean? The amount of heat absorbed by substance is directly proportional to its mass. Q directly proportional to M. Okay? So I will explain this once again. No need to worry. Then relation between heat and temperature. Just a minute. Let me pause this for a moment. It is overlapping. Okay. So let me continue. So minutes left. Just a minute. Let this activity play out. Just a minute. So, this activity 1 minute children. Yes. So already we played it till here. I'm going to continue showing. Just a minute children. System is start. It's taking time. Just a minute. Just a minute children. It got stuck. Just a minute children. Let's stuck with this. Please give me some time. We'll restart. Just in seconds I will restart children. I'm sorry for the delay. I'm extremely sorry for the delay
Sir, we'll
children.
conclude, no issue.
Ma'am, 5 more minutes ma'am.
Okay.
I'm sorry. So we have already seen till here children. So the 200 grams water is taking more time than 100 grams of water. Okay. So the quantity of heat is directly proportional to its mass. This we have already seen. This we have already shown to you. So take some mass of water in a beaker and with the help of a stand, place it on the tripod. With the help of spirit lamp, heat the water. So as you heat the water, what happens? Its temperature begins to rise. And you note down the temperature, children, one by one. So as it heats, what happens? Now observe the temperature changes in regular intervals while heating the water. We can notice that the temperature of rising with the time with constant supply of heat. So for the same mass of substance, the change in temperature is directly proportional to the amount of heat. That means that if you see carefully, the amount of heat gained or lost will be directly proportional to three things, children. This we have to understand like this. I will explain in a moment to all of you. If you see carefully, we saw that Q is proportional to mass. We also saw that Q is proportional to change in the temperature. That means more mass, it will require more heat to get heated. Like that, if more change in temperature is required, more heat is required. That means Q will be proportional to actually M into delta T. And I can write this as M into S into delta T, where S is called the specific heat of the material. Actually, in our activity, we saw that heat is dependent on the nature of the substance. That means heat is dependent on three things, children. Mass. Second one, it is dependent on change in the temperature. It is also dependent on nature of the substance. Okay, it is also dependent on nature of the substance, children. So on these three factors, heat is dependent. So we can tell that Q is equal to M into S into delta T, where M is a mass, S is a specific heat, delta T is a change in the temperature. Okay, and S is the specific heat of the substance, also called as specific heat capacity of the substance. So amount of heat gained or lost, Q is Ms delta T. SI unit of heat energy is of what? Joule. Everybody know that because it's a form of energy. And it can be measured in calorie also, children. Heat can be measured in calorie also. 1 calorie is how much? 4.184 joules. Okay, please remember. Now, using the definition learned earlier, let us define specific heat capacity of the substance. Specific heat capacity of substance is S is Q by M delta T. Okay, we know already formula, just now we wrote. What is the formula we wrote? Tell me, Q is equal to MS delta T. Right or not? Q is equal to MS delta T. And using that particular formula, I can write, so Q is equals to, already are having MS delta T. So therefore I can write S is equals to, bring that M and delta T this side, Q by M delta. Okay, so Q is measured in joules, children. So joule by M is measured in kg. Change in temperature is measured in Kelvin. So SI unit of specific heat will be, if this kg goes to the top and Kelvin goes to the top, numerator, then I will get units as joule, kg inverse, Kelvin inverse. Okay, all of you? So specific heat capacity of a substance is the amount of heat gained by unit mass of substance per unit change in its temperature. Okay, so if M is taken as 1 kg, unit mass means 1 kg, and unit change in temperature means 1 degree change in temperature. So if M is 1, if M value is taken as 1 kg and delta T is taken as 1 degree change in Kelvin, then S value will be equal to the amount of heat gained by unit mass of substance per unit change in temperature. So SI unit of specific heat is Joule kg inverse Kelvin inverse. Here I want to tell one important point. Specific heat is different for different substances. Children. In the textbook, the values are given. You can refer. Okay, and water has the highest specific heat in all the substances. That is the reason why when you are cooking also, if you see, if you heat oil in a vessel and water in a vessel, which will get heated fast, oil will get heated fast. Same quantity, 1 kg of water you take, 1 kg of oil you take in two vessels and start heating. Automatically you will observe that water gets heated fast, water gets heated slowly, oil gets heated very fast because oil has very less specific heat. So substances which have lesser specific heat require less heat to get heated. Substances which have more specific heat require lot of heat to get heated. That is the importance of this. Okay, so let me wind up this topic by explaining specific heat importance in daily life, children. Last and final topic for today. You have already seen that when you are having a samosa, a hot samosa, when you compare the outside, inside of the samosa, that potato will be very, very hot. Yes or not? What is the reason for that? The boiled potato will have water in it, and water specific heat is very, very high. Right or not? So it retains heat for a lot of time. That is the reason, children. Okay, because water specific heat is very, very high. Similarly, utensils also, you see different types of utensils. You have copper bottom utensils, you have normal vessels, right? So normal vessels and copper bottom vessels. Copper bottom will get heated faster, yes or not? And you see lovely example of sea. During daytime, what will happen? A breeze will be blowing from sea to the land. A nice cool breeze will be blowing. Yes or not? So what is the importance of this? Let me explain. Okay, just 2 minutes, children. You know that this is sea, let us say. Okay, this is land. This side land is there. Okay, you know that in the sea water will be there. This water specific heat is high. Water specific heat is water specific heat is very high. It has maximum specific heat, children. Whereas land specific heat is less. So you tell me, during daytime, who will get heated fast? Land will get heated fast. And whatever air is there on the land, the air will get heated and it will rise above. So when the air goes up,
Sir, please conclude.
yeah.
And you did not share your screen, so we are unable
Oh,
to
I'm
see.
sorry, sorry, ma'am. Sorry,
And
ma'am.
please conclude. One more meeting is there.
I'm sorry, ma'am. Extremely sorry. I'm sorry. Extremely sorry.
Hello.
I'm sorry, children. So
Sir, we can
I'm
show
giving.
it in
I'm
the next session, sir. We
Yes,
can
ma'am.
show
I
it
will
in
show
the
it,
next
children.
session.
I will show it in the next session, children. These are the last two questions for your answering. Okay. We have learned about Charles' law. We have learned about Boyle's law. Please go through the session. Thank you, madam, for giving this opportunity. Thank you also. Good day.
Thank you, sir, for the wonderful presentation. And with all the images and with all the videos, experimentation, children have benefited a lot. And thank you. And we are expecting the next sessions, more such interesting sessions from you. Thank you, sir.
Good enough. Thank you, children.